Okay, so good afternoon, everyone. This is session 2, ASP and Logic Programming, session 2. I'm Rachel Ben Eliyahu Zohari, and the co-host is Matthias Knorr. And I'm talking to you from my office in Jerusalem. So let's start with the first talk. The paper is a paper by Flavio, Everardo, Markus, Hecher, and Ankit Shukla, titled An Approximate Model Counter for Answer Set Programming. And the speaker is going to be Flavio Everardo, please.
Well, hi everyone. Well, I wanted to go to Greece, but well, maybe will be another time. Currently now I'm here in Mexico. It's 6 a.m. here, and I'm happy to be here and give you the talk. So I'm going to just put full screen mode here. Yes, okay. I hope that everyone can see it. And thanks for the introduction. Today I'm going to talk about an approximate model counter for answer set programming. It's working together with Markus, Hecher, and Ankit Shukla. And what I'm going to talk about briefly is an introduction, and also to motivate a little bit what is this work about, and some of the basics and preliminaries of behind this work. I'm going to then talk about the approximate answer sets count, discuss briefly some of the experiments that we have done so far, and discuss a little bit of the challenges and upcoming work. So from the introduction, well, of course, this session is about answer set programming, and logic programming. So I'm not going to dive a little bit in what ASP is, but just to say that it's, of course, a declarative framework well suited for problems in the area of knowledge representation and reasoning, with proven success in both the academy and the industry. And nowadays we have efficient ASP solvers computing, well, not only one solution, you can ask for several, but also with different reasoning modes. However, well, still no intense studies on counting answer sets or sampling or something among these reasoning modes, and this is also part of this motivation. And this is completely in contrast to what all the people in the community of SAT has done. There's several applications now, and where some of them uses parity or XOR constraints, which is something that we also use here. And also, well, it's worth to explore that for several applications in the ASP domain, approximate counting might be sufficient rather than calculating an exact count. So what we present here is an extension of the Klingo-based system Zorro towards an approximate answer set counting. We follow an algorithm called the Approximate from Chakraborty, Mill, and Bardi from 2013. This is the first implementation of this scalable model counter algorithm. And nowadays, with the advanced interfaces from the ASP solver Klingo, and benefiting also from sophisticated solving techniques from the XORs in the area of SAT, we have everything to combine and bring the best from every part into ASP. And for this initial work, this initial attempt, we're looking for accuracy and not yet for guarantees or scalability. So we're more interested in that we are really good approximating our counting. So as I mentioned, well, we're departing from parity or XOR constraint. So just to briefly talk about what a parity constraint is in ASP, well, it's a little bit of the formalities where top and bottom are the constants true and false, and the exclusive or the XOR of the atoms A1 and A2 is denoted by this expression, which is true with only one of both is true, and both cannot be true, or also none of can be false. Both cannot be false also. And we could generalize this expression from a series of n atoms from A1 through AN. It's a series of this expression.
Flavio?
Yes?
Flavio, sorry to interrupt. Are you changing slides?
Yes.
Because we see only the first one.
It says resume share. Okay. It says some past. Can you
Oh,
see?
now we see the others, yeah.
Oh, I don't know what's this. Okay, sorry, I'll just to continue from here, just to say that exclusive XOR for parity constraint of the atoms A1 and A2 is denoted by this expression, and we generalize it from A1 to AN in this form, and this is satisfied if and only if an odd number of atoms among A1 through AN are true, and so we can refer it to as an odd parity constraint. To express the opposite, in this case, the even parity constraint, we add the constant top in this expression. So in order to satisfy the A1 XOR A2 XOR top, we have here in this case, both A1 and A2 must be true or both must be false, and the same applies for the general form of an XOR constraint. So why these parity constraints or XORs are used in this work? Well, nowadays we have this system Zoro, which is these parity constraints are the fundamental blocks for this tool, and nowadays the system has different means for implementing and preprocessing these parity constraints. And we have now as we made it by theory atoms following the aggregate-like syntax, amount to the XOR operator following the classical XOR operator properties. But they act as a filter, as an Hecher set filter, and this is nowadays they act as directives, meaning that they cannot occur right now, neither in the body nor in the health rules. But they are perfect for reasoning modes like sampling or counting. And just to mention a little bit how it looks into ASP. Logical XOR, for example, of P of 1 XOR bottom, which is a unary XOR constraint, we can represent it as this theory atom with the identifier odd in this for this particular expression with the terms and conditional literals, and the same applies from a P of 2 XOR P of 3 XOR top. We will just write it as even, and well, of course, well, I'm going to detail a little more about this XORs in the next example. Just to review how the XOR constraints partition the search space is something that is the key behind this work. If we have a simple or basic ASP problem from an unrestricted choice from P of 1 to P of 3, we can enumerate all answer sets, and we have these 8 solutions. If we add the first XOR constraint and we solve it on top of this program, we can filter the answer sets with that where P of 1 is not true. So it's just so I will just get in the fourth solutions from the second half of this image. The second constraint in this case for the domain of P of 1 to P of 3 could be instantiated as an even of P of 2 and P of 3. So it cancels all the answer sets where P of 2 appears but not P of 3, and vice versa, P of 3 appears but not P of 2. So it's just playing around with the combinations of P of 2, P of 3 being true, or P of 2 and P of 3 being false. The conjunction of these two XOR constraints will give me that the only answer sets are P of 1 and P of 1, P of 2, and P of 3, solving these XOR constraints of this program. So in a more general way, we have in this case a non-symmetric search space, solution space, an XOR constraint divided search space roughly by half. And if we add one parity constraints, we're dividing the search space roughly in 2 parts. Well, half in 2 parts may be not exactly the same size, but this is what we are striving for. And of course, this is what happens when we are n parity constraints. We're just cutting this search space, and for these purposes, we need to pick a small random cell or cluster, which could also be a synonym for this, so we can sample or count this. So talking a little bit about approximate answer sets count, of course, the motivations that a priori we don't know how the distribution of the solution set is, and we need to answer this type of questions of how to perform a good hashing if we have no knowledge of the distribution of solutions, or how can we partition the search space as mentioned in the slides before, that are roughly equal, the same size, they contain the same, more or less the same number of solutions. Well, the key for that is universal hashing. And we're talking about universal hashing. The key idea is that to pick a function randomly from a family of k-wise independent hash functions. And the point is to randomize over arbitrary input distribution and guarantee low collisions in expectation to how the data is chosen. We pick 3 wise independents, and what we achieve here is that with high probability, we get random cells which are small enough that we can also call almost uniform generation. And the scalable approximate model counter for ASP is because has its roots on this work from Chakraborty, Miel, and Barty, 2013, called Approximate, and relies on a number of models giving a tolerance and a confidence. These are the only 2 input values that the user needs to introduce. So it's with a confidence, let's say, of an 80%, and a tolerance of how up or down from this 80% I would like to have my approximate count. And these are this is what we need to calculate the number of solutions. Given these values, we calculate a pivot value to check if a cell is small enough, and the algorithm runs t times depending on the delta value. I'm going to explain a little bit later about that. And we keep partitioning the cell, if it's not small enough, we add another XOR, and this is repeated to get one of the following solutions. Either a cell is not empty and small enough so we can start counting, or the cell is empty and this run is discarded and we check it, we do another run. These are the algorithms for us, that, of course, I'll invite you to read it from the paper. I really don't want to dive but I would prefer to explain in a different way how this works. So we calculate a constant pivot value, and first we ask for pivot plus 1 answer sets. Let's say that, for example, from a solution space, I don't know, well, 100 solutions, and let's say that, for example, our pivot is 50. So we ask for 51 answer sets in this case, and we cannot guarantee that all the answer sets are under this pivot value. So, so we will have to add XOR constraints. But if the total number of answer sets is less than the pivot value, we'll return the exact count and we finish the run. If not, well, this is what happens in the next slide. And as I said before, we keep adding what parity constraint. We pick this random cell and ask again if the number of answer sets is less or equal than this pivot value. If not, we keep adding another XOR constraints, pick a random cell, and you can keep doing the same until we can guarantee that now the number of answer sets is less or equal that pivot value. So again, we run this t times, and this is also and for each run, if a cell is not empty and small enough to count, or the cell is empty, it could be unsat, this run is discarded. But if it's satisfiable, we add the number of answer sets to a list, we call it C, and the approximate answer set count is the mean of this list C. So talking a little bit about the experiments, just briefly talking about the setup, we tried random instances over different ASP problems, most of them including graph-based problems. And we began with easy to solve instances for Klingo. Sorry, what we mean here with easy to solve instances is that we wanted to make sure that all these Klingo can enumerate all the solutions without printing under 10 minutes. So we can have a reference to validate the accuracy of our count. And now we're not considering performance scalability, so we're just focusing, as I said, the quality count, the counting of the quality of the counting. We run it sequentially on a modest laptop with Linux and Python just to prove the concept. And each benchmark instance was run 5 times without any time restriction. For this presentation, I have two of the problem classes here in the slides. For this first one is the graph coloring, where here on the left we have 10 instances. Here are the number of answer sets here in the second column, and then we classify from the best and the worst from the 5 runs that we from each of the instances. Here we calculate the median, we also the mean, and this Q factor or quality factor is how close or far we are from the target. In this example, we can see that here, for example, the mean it's quite close to the number of answer sets. So, and on average, we're just our best approximate count is quite close to the exact count. In the worst case, we're a little bit overestimating, and the median, of course, has a little bit more of deviation in terms of our approximate estimation. From the second, this problem, the subset minimal vertex cover, also with the same pattern. Here we have the number of answer sets here on the left, and here, of course, in the best cases, both the median and the mean return quite a really good approximation, even very, very close to the exact count. But also here, with the worst case, we really have no, not so significant deviation. Also, in our worst case scenario, the approximation was really good. And well, of course, we have we have solutions that are quite accuracy in terms of our counting, but of course we have some of them quite low. For example, the instance 4 in our worst examples was under 70% of close to our counting. So this is part of what we have to tune afterwards. So just talking about the challenges and upcoming work, of course, well, we have to provide guarantees for ASP that not necessarily are the same that are proven in SET. Of course, check scalability over more complex instances. Here, our let's say our solution space, our biggest solution space, this is big, but this is not quite hard to solve for Klingo or even with parity constraints on top. So this is why we have to test more complex instances, more bigger and dense solution space, but also with problems that are more challenging than the ones that we choose. Also, class enumeration is very efficient. So this is in order to have a chance to solve a program and then on top extra constraints, we need to identify with a phase transition from parity constraints. This is a task from Soro. And one of the reasons behind this is that in Soro, we proved that there were some
I give up as a session chair. If there is anyone from this paper, one of the co-authors, if there is someone from the co-authors who can answer questions, I'll be happy to ask. But if not, we can skip it for this time, and maybe we can ask him later. Maybe he will rejoin us in the future of this session, because he did present most of the paper. I think we missed only the conclusions. And future work and something like that. So I think we will proceed to the next talk. And just a moment, let me find it. Okay, so the next talk is a paper by Jorge, Fandinno, and Markus Hecher, Treewidth-Aware complexity in ASP. Not all positive cycles are equally hard.
Hi, my name is Markus, and I'm presenting Treewidth-Aware complexity in ASP. Not all positive cycles are equally hard. This is joint work with Jorge Fandinno.
So what is this Treewidth all about? Well, in general, there are lots of problems that are rather hard on arbitrary graphs, but these problems typically become rather simple if we look at the special case of a tree.
Well, and the Treewidth now is a way to measure the closeness of a given graph to being a tree, or the tree-likeness of a graph.
While Treewidth was originally defined for graphs by Robertson Seymour in a series of papers, nowadays having bounded Treewidth K can be seen as one of the most cited combinatorial invariants. In fact, assuming instances of Treewidth K renders a large variety of NP-complete problems tractable. We call this tractability fixed parameter tractability since it depends on fixing the parameter Treewidth K. In such fixed parameter tractable or FPT algorithms for Treewidth, the complexity or the hardness of a given problem is confined to this parameter Treewidth. This allows for a more fine-grained analysis where we get polynomial runtime, but in addition the runtime also depends on the value of a function depending only on the parameter Treewidth k. In classical algorithm analysis, where we do not have this fine-grained tool, we often only consider instance size and cannot confine the hardness of a given instance to some parts.
There are plenty of these FPT results for several problems. We have single exponentiality for Boolean satisfiability and even counting the number of models of a given Boolean formula. For normal or head cycle free programs, there are algorithms that require slightly super exponential runtime in the Treewidth. There are also lots of FPT results for problems believed beyond MP, like deciding the consistency of a disjunctive ASP program. This can be decided actually in double exponential runtime in the Treewidth. And now what maybe is a bit surprising is that there are actually frameworks and solvers that apply Treewidth for solving problems. On the one hand, they are quite generic frameworks, but even some of these frameworks manage to solve instances up to Treewidth upper bounds of more than 200. And then there are even highly optimized solvers for solving specific problems. Okay, but what's the issue then?
Well, as you may have guessed or noticed, the functions in K have a really bad worst case. Well, and if you do not believe in complexity chaos, you would agree that the polynomial f of k is probably not possible. But what's even worse than these worst cases is that there is not much hope to improve these f of k's. Unluckily, this is also the case for deciding the consistency of a normal ASP program.
If you want to skip or delay lunch break on Wednesday, you're highly invited to join my talk at the GR conference where I explain details. From a high-level perspective, this result expresses the following. Under reasonable assumptions in computational complexity, deciding the consistency of a normal ASP program is expected to be slightly harder than deciding the satisfiability of a Boolean formula in terms of Treewidth. So while SAT can be decided in single exponential time in the Treewidth, this is not expected for deciding the consistency of a normal ASP program. If one aims for an algorithm polynomial in the number of atoms, one probably has to live with slightly super exponentiality in terms of Treewidth. Observe that this lower bound result immediately carries over to larger fragments of programs like head cycle free programs. So this is it, right? Or is it? I mean, is it impossible to decide the consistency of a normal ASP program in time slightly better than super exponential in the Treewidth? No, not quite.
But how? Well, we just consider an additional parameter.
In this work, we consider not only the Treewidth, but in addition also the size L of the largest strongly connected component of the dependency graph of a normal program. Intuitively, the dependency graph captures the directed dependencies between the positive body atoms and the head atoms of a rule. This yields to an algorithm that is still slightly super exponential, but we have a runtime 2 to the k log lambda, where lambda is the minimum of the Treewidth k and the size L of the largest strongly connected component of the dependency graph. Further, we also present a Treewidth-Aware reduction from head cycle free ASP to tight ASP, where we only slightly increase the Treewidth. This increase is from k to k log k.
Since this reduction is Treewidth-aware, what it actually does, it simulates parts of dynamic programming by guiding the evaluation or the overall reduction along a given decomposition for Treewidth. Unfortunately, the increase of Treewidth, which is caused by this Treewidth-aware reduction, cannot be avoided, at least not if the largest SE size L is polynomial in the Treewidth. Finally, we present the Treewidth-aware reduction from tight ASP to Boolean satisfiability, where we only cause linear increase of Treewidth, which also establishes that tight ASP has about the same complexity for Treewidth than SAT. So what has been done so far?
In the early 2000s, the ETH was proposed.
The exponential time hypothesis, or ETH for short, implies that we cannot solve satisfiability of a given formula in better than single exponential time in the number of variables in the worst case. And while this ETH is widely believed, it's actually stronger than P is not equal to NP. So it might be the case that ETH fails, but still P is not equal to NP.
Since then, the ATH has been used to show conditional lower bounds for, let's say, loads of problems and also for several ones believed beyond NP. For ASP, the parameterized studies that have been conducted so far mainly concentrate on upper bounds. Besides Treewidth, for example, already the number of even and or odd cycles was considered, as well as the smallest number of atoms that when removed from the program lead to a certain property or a certain target class. Further, also, multiple combinations of parameters were studied. This brings us to some preliminaries. Since I guess most of you are familiar with ASP anyway, let's just briefly recap some basics. A program is a set of rules where each rule consists of a positive body, a negative body, and a head. The AI and BJs are atoms or Boolean variables, and the negation here means negation as failure or default negation. There are several prominent fragments. One is normal ASP, where each rule only has one head atom. A normal program is called tight if there is no cycle in the positive dependency graph of the problem, where the positive dependency graph depicts the dependencies from atoms appearing in the positive body of a rule and atoms appearing in the head of the same rule. An ASP program is called head cycle free if there is no cycle in the positive dependency graph program involving two head atoms of a rule. Now, for a set of atoms to be an answer set of a head cycle free program, first of all, the set of atoms has to be a model of the program, and each atom that is in the model has to be justified or proven. Such a justification is done via level mappings, where each atom gets assigned a level from 0 to the number of atoms minus 1. Intuitively, an atom A is justified. There is a rule with the atom in the head requiring to put this atom to the set M, such that all the positive body atoms have a smaller level than the level of A. Consider the following program. Let's now quickly analyze the positive dependency graph of the program. So we draw an edge from D to A to B, D to B, E to B, B to C, as well as B to D and C to D. Observe that the program is head cycle free since there is no cycle involving E, F, or G. One answer set, for example, consists of E, B, C, D, and A, and the levels can be assigned in that order. So let's now come back to this tree width, or this measure of tree likeness of a graph. Well, in fact, tree width can be defined in terms of tree decompositions. A tree decomposition of a given graph is an arrangement of the graph into a tree, where each node of the tree, referred to as bag, gets assigned certain vertices of the graph. This has to be done in such a way that the following three properties are satisfied. First of all, every vertex has to occur in at least one bag. In our example here, we see that this is the case for all the vertices of G. Then all the edges have to occur in some bag, meaning that for an edge, the two vertices of the edge have to occur together in at least one bag. Here we see that this is the case for the edge AX, BX, and AB, but we can check that this is true for all the edges of G. Last but not least, we require the connectedness, which basically ensures that if we restrict the tree to a certain vertex of the graph, the result is still connected. In our example, we see that this is the case for C, also for B, and for X, and finally also for vertex A and Y, since both vertices occur only in one bag. So this is indeed a tree decomposition of our given graph G. The width of a tree decomposition corresponds to the largest bag size minus 1, which is 2 in our case, and then finally the tree width of a given graph G is the smallest width among all potential tree decompositions of G. The last missing ingredient we need before talking about details of our reduction is so-called dynamic programming on tree decompositions. So how does this work? Well, first we assume a given propositional formula. Then we compute the tree decomposition, but for that we need a graph representation of the formula. Here we use the so-called primal graph, where as vertices we have the variables of the formula, and we have an edge between two vertices whenever the two variables occur together in at least one clause. Similarly, this can be done for ASP programs, where we have as vertices the atoms of the program, and we have an edge between two vertices whenever the corresponding atoms appear together in at least one rule. So assume the given tree decomposition, which you already know, of the primal graph of the given formula. Then dynamic programming on the tree decomposition performs a bottom-up or post-order traversal of the tree
and computes for each tree decomposition node a table. Whenever we introduce a new variable that has not been seen in the current subtree during the traversal, we need to guess a truth value for the variable. In the leaf node containing bxa, we need to guess 2 to the 3, so 8 many truth assignments, and then we check the corresponding clauses of the bag, meaning not A or B or X and A or B. This leaves us with 5 rows. This is then continued for the next node, where we take the previous table, project it to B and X, introduce C, and check all the clauses that only use bag variables, which leaves us with the next table.
We continue like that and compute the tables until we reach the root node,
where we have to merge agreeing assignments. Since the root table is not empty, there has to exist a satisfying assignment, which can be easily reconstructed by following back predecessors of rows. With this technique, we obtain an upper bound for Boolean satisfiability, which runs in time that is single exponential in the tree width. This technique can be extended to solve head cycle-free ASP, even when considering the additional largest SCC size L. However, also our Treewidth-Aware reduction is highly influenced by this dynamic programming technique. So we have collected now everything to discuss our reduction from head cycle-free ASP to tight ASP. Okay, so what has been known for a long time is that positive cycles are somewhat responsible for the hardness of evaluating programs. However, in the classical complexity, these cycles are mainly an issue if one wants to preserve all the answer set, and still this only causes a subquadratic overhead. In the parameterized context for tree width, while the situation might look similar, the problem is actually a different one. The main issue for tree width is that there could be lots of positive cycles which are well spread across the tree decomposition. So in these parameterized algorithms, where we do dynamic programming on top of a tree decomposition, it could be the case that we have lots of cycles and we only see the cycle in parts. It's a bit similar to moving a magnifier along a large cycle, and you're only allowed to look at the magnifier basically, so you only see at once parts of the cycle. And what we also have for these tree-width-based algorithms for ASP is that if we only have cycles of length more 3, then it's not an issue. So we basically are single exponential in the tree-width in this case. The reason for that lies in the properties of a tree decomposition. So if we only have cycles of length 3, it is guaranteed by the properties of a tree decomposition that these cycles are actually analyzed in one tree decomposition node. So we do not have the case that the cycle is well spread. So can we generalize this somehow to larger cycles? Our initial approach is to additionally also consider the largest SCD size L. So we take a head cycle-free ASP instance of tree width K and largest SCD size L, and we construct an ESP instance of tree width K log L and SCD size 1. So the resulting program is tight, and what's quite nice is that our reduction also preserves the answer sets bijectively. It also works for counting and, for example, enumerating answer set. Note that since the reduction is Treewidth-Aware tree decomposition guided, it actually uses a decomposition. Such a decomposition can be computed either heuristically or by using an approximation. Our approach uses level mapping similar to related work. So for each atom A, we have a potential level from 0 to the SCC size of the atom minus 1. However, in order to preserve tree width, we still need to evaluate the program in parts. So for each tree decomposition node. And it is quite important that we guide the justification or provability information of atoms from the leaf nodes towards the root, so the information is guided along the decomposition. In the following, we try to give a simplified view of our reduction from a head cycle-free program to a tight program. Let therefore pi be a head cycle-free program and T and he be a tree decomposition of the primal graph of this program pi. Now we construct for every node of the decomposition the following rules. So we guess for each atom of a bag where it shall be set to true or to false, and we check all the rules contained in a node T. Since we are doing these first two roles for every node T of the decomposition, ultimately this boils down to computing models of the program. Whenever we encounter in a node T a rule where an atom X is in the head of the rule, we actually have to remember if X is proven or justified in node T. If X is set to true, and this is actually the case, and if all the positive body atoms of the rule of the same strongly connected component have indeed a smaller level mapping than the level of X. Note that for simplicity, handling the level mapping is left out. Next, we need to propagate this provability information. So if in a node T an atom X is proven, it is actually proven for T and upwards. If an atom X is proven in a child node of T, it is also proven for T and upwards. Ultimately, we need to ensure that all atoms that are set to true are indeed proven. This is ensured for the provability atom for X and the node T prime where X is removed. If no such removed node T prime exists, this means that the atom X is still present in the root node of the decomposition, and therefore one needs to check this provability for the root node. In the end, the properties of a tree decomposition, as well as the overall construction of the reduction, which means guiding this provability along the decomposition, similar to dynamic programming, ensure that the reduction is correct. However, for bijectively preserving all the answer sets, we need to add two additional rules where we basically specify if we set an atom to false, it is not allowed to have a level that is larger than 0. Further, it should not be allowed to justify or prove an atom with a level that is smaller than the current level X has. With this reduction, one can show that actually the answer sets are bijectively preserved. So for each answer set of pi, there is an answer set of the resulting program. Further, the reduction is actually Treewidth-Aware, and it's designed to keep the increase of treewidth as little as possible. One can show that the treewidth of the resulting tight program is actually bounded by k log L. And in fact, under the exponential time hypothesis, this increase of treewidth cannot be significantly improved for L that is polynomial in k. In the paper, we also discussed the second reduction, which goes from tight ASP to Boolean satisfiability. And the idea of this reduction is rather similar to the previous reduction, but we do not need a level mapping, of course. And what we basically do is we guide task completion along the tree decomposition. So intuitively, again, for each tree decomposition node, we check that all rules are satisfied. If we set a variable X to true, we need to ensure that we have ultimately provability in the node where X is removed or in the root node of the decomposition. We have provability in a node T for X if and only if there is a rule with X in the head that actually forces us to set X true. And finally, we have to define that if we have provability for X above T, that we have it either in T or somewhere below T. If we weaken the last two occurrences of equivalence to implications, we do not preserve the answer set, still the reduction is correct in terms of preserving the decision answer. This already brings me to the conclusion. In this work, we studied Treewidth-Aware complexity for normal ASP and head cycle ASP, where besides treewidth, we also consider the largest SCC size L. More concretely, we present a Treewidth-Aware reduction from head cycle free ASP to tight ASP, which is guided by a tree decomposition, and where the treewidth is only increased from k to k log L. It turns out that this increase of treewidth can probably not be significantly improved if the largest SCC size L is bounded by a polynomial in K. The paper also contains a reduction from tight ASP to Boolean satisfiability, although here we did not have much time to discuss this in detail. Currently, we are still in the progress of implementing our reductions, and we hope that these reductions might be fruitful for treewidth-based solvers, especially in the realm of counting or projected counting. For the future, we suggest to improve for the case if L is extremely larger than K and not polynomially bounded by K. Further, a deeper study on the actual runtime of our reduction depending on K and L, as well as conditional lower bounds for K and L for all the cases, might be beneficial.